All right, that said, let's go ahead and get started. Oh, that's the wrong thing. I thought some of y'all might appreciate this. Give you a good little laugh. I'm sure y'all know what I'm talking about. There were quite a few with some stupid answers. And for those of you that stay after class, you'll see for one of the problems that had a stupid answer, I think there were like 6 people that picked it. Maybe they just, they felt like they were low on time, but hey, at least maybe you got some good laughs out of them. And don't worry, when we get to those stupid answers, I'll explain why they're wrong. I'm sure many of you got the question about the Dean of Gender Studies. I think option D or whatever said we are 95% confident there's no Dean of Gender Studies. That's incorrect because we're 100% confident. So that's why that one's wrong. But enough with that. Let's get into our regressions and correlation coefficients. The variable stuff, I am very sure you've seen this before, pretty likely in a science class. The way I think it's easy to define, at least for this class, the dependent is the output, the independent is the input. I personally find that the easiest way to understand it. For the regression stuff and the correlations, you'll probably find that to be the easiest one. Basically, one of them is causing or explaining the difference in the other. Now notice I don't say just causing, I say causing and explaining, because you can have something not cause something, but still explain it. For those of you who are more on the pure math side of things, which I'm sure is very few of you, I'm sure that all of you have seen the f of x notation at some point. You can use that as well, because the nice thing about f of x makes it very clear what the input is, because you don't have f of y here, we have f of x. Now you'll see an f of x comma y later, but that's just for using Desmos. So that said, the main box that matters here is the second one. The first one is just a concept box. You don't need to write the first one down. The second one is the one that matters. And the idea behind a linear regression is that for our data points, we can draw a best fitting line that can predict these data points. And obviously it's a line, you'll recall from high school algebra, maybe middle school math, that this is just intercept plus slope times x. If you understand that, then you're gonna have to rewind time by about 10 years, go relearn that. Now, the new thing here is you'll notice, and I'll zoom in so you can see it about as clearly as possible. That is not a Y, that's a Y with a little hat on top. We call it a hat, you can call it a carrot, whatever you want. It looks like this. The reason why we say Y hat is because that is what we are predicting to be the Y value. It's not necessarily the actual Y value. It might end up being the same as the Y value, but not necessarily the same. Now, I will show you how to get these, and I will be fully upfront. We use regressions a lot, both in the course and on the job. This unit is the crux of applying this course. So the thing is, though, when you actually do these regressions, you can have a computer do a lot of the math for you. And so when it comes to these regressions, I'm going to assess concept more than anything else. You'll have some calculations, but I'll show you a way to streamline those calculations by a lot to save you a lot of time. So before I continue, does everyone have this written down or can't read anything or blah, blah, blah? Okay. So don't worry about the stuff on the right. Look at the left for now. Let's say I could draw a line like this. I could draw it like this, or maybe if you are a sadist, you can draw it like that. But the question is, what makes one line better than the other one? Now, you might say, oh, well, the second one is closer to the data point. So what does that mean? And in this case, the general idea of any kind of line, if you want it to best fit the data, you have to define what best fit means. Generally speaking, as I just said, you want it to be as close as possible, but how do you measure closeness? Well, the way you can measure closeness is the obvious one, distance. The thing is, though, there's a lot of these distances, and distances are squares. Well, you take the square root at the end, but Generally speaking, you're having squares at some point. So minimizing all of those squares gets very tedious. And let's just take this first line. It's not the correct one. Let's get the correct one. Let me pull out my straight line. There we go. So let's consider this point and the distance between this point and the line. That is called the residual. The residual, the distance between a point and its predicted value. That'll come up on the web work. I don't put it on the exam because this is implicitly taken care of on the exam, but there will be a definition question like this on the web work. In essence, we use the residuals in the process of figuring out our regression. Now, we want to minimize this distance. It's absolute value because you can't have a negative distance. By definition, you can't. I mean, if you want to, you can try to go quantum physics on that stuff, but this is math 2345, not physics 50 million. So we have that absolute value. The issue with that is, let's suppose we had this. Here we go, let me pull this up. What do you mean B of 0? Oh, up here? That says B0, yes. We got B0 and B1. Sorry, it just wasn't popping up for whatever reason. Okay. So now let's suppose we draw this line right here. The distances up until our very last point, so let's say I drew a squiggly right here. Everything to the left of the squiggly, the dots are all pretty close to both the lines. The last one, they're very different. And that last one's not good because compared to all the rest of them, that's a very large distance. And so the idea behind the criterion we use here is if you have a regression line, whether or not it's the correct one, you get a big penalty on the correctness of that line if you got a point that's really far away from it. And so if you got a point that's really far away, squaring it makes it more of a penalty. And that's the conceptual reason for why we're going to use least of squares. There's a calculus reason. This isn't a calculus class. If it was, then I'd spend 30 minutes explaining why, but it's not. So we'll just go with that. So the idea behind least squares, and I will zoom in so you can see it about as easy as possible. We want to minimize the squares of our residuals. Remember this yi minus the y hat? That's the residual. We want to minimize the sum of these squares. Now, you might ask, okay, that's fine. How do I do that? Trial and error? I can't test 5 million lines in 5 minutes. We only have 90 minutes on the exam. Well, the nice thing is you can use, this is actually multivariable calculus now, but you could use multivariable calculus to optimize this and find the method. I will just show it to you. And don't worry if you don't have this whole thing written down, because what really matters is this one. This is how we get our regression equation. This is the big bucks. And I'll show you the Desmos shortcut to save you quite a bit of time in a moment. So you always calculate your B1 first. So here the yi minus, now notice we have the y bars. You might say, why do we have the bars? And to give you a conceptual reason, let's say we have our data here. Let's say we got one there, and one here. The reason why is because by definition, an average is supposed to be a good reflection of the center point of the data. If instead of using our averages, we used one of our data points, what happens if that data point is an outlier? What happens if that data point doesn't perfectly match the regression line? And the idea behind using the bars, or well, X bar and Y bar, which are our sample means, the idea behind using those is that the sample mean is more likely to be accurate than any individual point. If you want a very clear-cut example, we keep going back to Georgia polls because they're good examples. We have 1,000 people. If you pick one person in that poll and they say they're voting for Biden and you take 100% as your point, that's nonsense. That's a very extreme example of why you might use the bars. So, and I will note, and to make it very clear, I'll put an extra little bracket here. You take any given point, find the difference between the point's two values and their respective averages, multiply those differences together. You don't sum up the products separately. You do them together, then you sum up all of those products. So you'll recall when we did the standard deviation formula, we had the differences, we squared them, and then we added up all the squares of differences. Same process here. You'll notice we have squares in the bottom. That's what you're used to. The xi is your data point, the x bar is the mean. You're used to this because you've seen this part before. For the top, what changes is we replace our second xi minus x bar with a yi minus y bar. If you're really interested in the calculus for why this is the case, they go over it in the textbook. You can go look at that. That's multivariable calculus. If you like that, you're more than welcome to take a look. Now, once you get your B1, getting the B naught is very easy because your y bar and your x bar by definition are going to be a point on your line because you're centering your line around it. If the B1, your slope comes from that sample mean and well, the two sample means, then your B naught should be coming from that. So in this case, we plug in. So in an overly simplified example, if you calculate your B1 to be 3, let's say we had B1 is equal to 3, and you had X bar is equal to 3. And let's say you had Y bar is equal to 4. Then you'd come down here, you'd have 4 minus 3 times 3, so B naught would be -5. It's not going to be that simple. That's just illustration of concept. Now for the WebWorks, you will use this process to compute the linear regressions. On the midterm exam, you'll get to use a shortcut. And that shortcut will be, I will give you the B1 and save you roughly 540 hours of time, give or take 540. But I will give you the B1 immediately. I'll go over the shortcut with the B1 for now. We'll assume I'm not giving it to you. For this, you can use Desmos as the shortcut. You don't need to put this on your cheat sheet. Oh, what's this? Go away. You don't have to put this on your cheat sheet, but it will be very useful to have for the WebWorks. So you want to compute your means of x, y. It says xm, ym. The m just means mean. You can say x bar, y bar, doesn't matter. It's just when you're entering it in the Desmos, just putting xm is a little bit easier to type. And what I will do here now is switch. Yes. Here we go. Oh, up here? You don't need to worry too much about this. It's more so that other box that's more important. Okay. All right. So we'll do this. I'll just share my entire screen. Here we go. So now I can switch between the two pretty freely. So what you'll do in your Desmos, the X on the keyboard, you know, the minus sign, you can make an underscore. So that makes it a subscript and I can put M. You have to compute that on your own, but you'll be dealing with integers. Not a big deal. No more difficult than it was in unit 1. Let's just call it 5, doesn't matter what. And you'll compute your Y. Again, you use the shift and then the minus becomes underscore. That's how you do it there. And I call that 5. That's your first step. That's the easiest part. Now, if we go back here, you can actually use this notation and you'll see why I use it in the moment. So we're going to let the f of x comma y equal x minus xm times y minus ym. And this, if I pull back up here so you can see it, that is this thing right here. That's part of the numerator. So, and to show you that it works this very easily, let's say your data point is 4, 4. F of 4, 4, it'll do it for you. No pun intended. Now, the next one, and much of this is just entering things in. You should have to know what to enter in for the WebWorks. The G is going to be the denominator. So we have the G is equal to x minus xm You can just square it, or if you want to write out the second one, that's fine. Again, that's our denominator. At this point, the next thing I do, you'll see I set t is equal to these sums of f's and b. The t means top. If you want to literally write in top, go right ahead. I just use t. B means bottom. So let's suppose that our 5 data points, or we'll just go with an extremely simplified example. Let's say we had 4, 6, 5, 5, and 6, 4. In this case, our top would be equal to, oh, why do I have 2 parentheses? We had the 4, 6, plus the 5, 5, plus the 6, 4. That's your numerator. Now the bottom, we just need the x's now, so that's the 4, 5, and the 6. And at this point, the last step until you get the B1 is top over bottom. And there you go, that's your B1. At this point, it's very trivial. You just plug it into the formula. As long as you know how to enter it in here, you'll be good to go. Now, I'll give you an actual real example from the web work now. So let me zoom out just a little bit. This one is straight out of the web work. So we have these 5 data points. The first step, and I believe those at home should be able to see this because I'm sharing the whole screen. Let's get the mean first. We have 0, -1, 4, 7, and 11. If you want to type it in the Desmos, you can. Doesn't bother me. You divide that by 5. So our X bar is going to be 4.2. Let me get rid of this for the time being because we don't have those points. Now, the Y bar, we have 0, 9, 13, 20, and 24. And we divide that by 5. So our Y bar is 13.2. Okay? Now, the top is just the sum of the 5 F's because we have 5 sets of data points. Our first one is -1, 0. Our second one is 0, 9. And the next one is 4, 13. Doesn't matter if it goes off the screen, doesn't matter as long as you type it in. Then we have 7, 20 and 11, 24. And the bottom is just the sum of the g's of the x's. So we had -1, 0, 4, and 7, and 11. It finishes the rest. That is our B1. If we round that to 3 decimal places, we get 1.810. So when you enter it here, you can put 1.810, but for the purposes of getting our B0, don't round this particular part till the end for the B0. If you want to enter this into Desmos, then you can. You know, the B0 is our Y bar minus B1 times X. So if you quite literally want to, you can literally, I'm there. You can literally put in B1 is equal to T over B if you really want to. And that means our B0 is equal to Y bar minus B1 times X bar. So the mean of our Y's minus B1 times XM. That's our B0. The 13.2 for Y, that is just averaging. It's the mean of our Y values. Y bar is the mean. So the 0, 9, 13, 20, 24, added them all up, divided by 5 to get the mean. So in this case now we have 5.599. Now as a note, you might ask, what would happen if I put in 1.81 in for this B1? You get it wrong. The web work's going to yell at you. He's going to say, that's not right. This is why I say do the plus or minus 0, 0, 1 on everything. This is one of those reasons why. Are there any questions about using Desmos to do these regressions? When you get really, really big sets of data, you can often have Excel do it for you. We're not going to worry about that. The point of these very small data sets is you get used to just the general idea of how it's coming out. So you'll have a couple of these on WebWork, but now I'm going to write this out in our form. So we have our predicted value is equal to our B naught, which is 5.599 plus 1.810x. On the exam, you'll get to do the shortcut, but you still got to write this out. You got to write the whole thing out. The two bars, you know, the X bar and the Y bar, or it could be different letters. You know, if you're dealing with grades, you might have G bar. If you're dealing with salaries, you might have S bar. It's just the bar means average, and you'll put it here. Now, let's suppose I took this, and this thing's getting overheated. Let's say I asked you to get, so here we have 0, 9. Suppose I ask you, what does this predict for x equals 0? Well, in this case, if we plugged in 0 here, this whole thing goes away, and we're left with that. Not a great regression. We're quite a few off. Yes, it'll say it on the exam as well, right at the top. If you use Desmos, you need to tell me what you're doing with it. You don't just get to say buy Desmos and skip straight to the answer. That doesn't count. You can use Desmos to skip the tedious work. You just have to tell me what you're actually doing. Now, as a note, the less data points you have, the less viable linear regressions are, simply because you don't have a large sample size and you're more prone to screwing up. Because when you have a smaller sample size, it's harder to figure out if any of the data points are outliers. Because if they're an outlier, it's going to screw up your whole regression. On the other hand, if you have 500 data points, doesn't matter if one's an outlier, it's not going to change it all that much. Because we recall, we're trying to minimize this. If we got 500 of these, unless that outlier is one hell of an outlier, even then it's not going to affect it all that much. That said, are there any questions about using Desmos to compute the linear regression the long way? Okay, I'll show you the short way later, but for now, you don't need to write any of these down. This is just concept. This, early on, we talked a little bit about covariance, but I just said I wasn't going to assess it. The reason why they brought up covariance is because you could use the covariance to calculate the correlation coefficient. This is the easy way to calculate correlation coefficient. This is how the computers do it. I'm not going to ask you to calculate this because the computers will calculate it for you. I'm just bringing you up the concept. So when we have our line, there's my mouse. When we have our line and we have a point here, we have this distance between the line. Part of that gap is caused by the regression line itself. That's called SSR. It's just the sum of the squares, basically the distance, the error, the screw up, due to just the line itself. Now, there's going to be a small part that's caused by error, because as you'll recall over here, we had this goofy looking E. That just means error. No matter how accurate a regression, you could have a perfect regression line that matches it perfectly. You can get one data point that comes in and just sucks. That's because of error. That's not because of your line. And obviously, the only differences you can have are from the regression or the error. So therefore, the sum of all those differences, we call this the total sum of squares. Now, this is how we calculate this. They call this the coefficient of determination. Just refer to it as R squared. You should know it's the coefficient of determination, but on the exam, and what I will call it going out, is just R squared. I will tell you what this R squared means in a moment, but this is where it comes from. Now, I believe there's a little bit of a multiple choice concept question involving this. Let's suppose, because obviously you can see SSR, let me pull it up. SSR has to be less than or equal to SST. And the reason why is because this can't be negative and neither can that. Both of these two are greater than or equal to 0. If they're both greater than or equal to 0, that's got to be less than or equal to that. So one key property of this r squared, and this is something you can write down, 0 is less than or equal to r squared is less than or equal to 1. So therefore, if we took the square root of r squared, we have 0 is less than or equal to r is less than or equal to 1. This r, that's the correlation coefficient that we didn't touch on in chapter 3. This is why I waited until here. You'll see even more clearly in a moment why I waited until chapter 14 to cover the correlation coefficient. The idea behind the correlation coefficient is that it explains the relationship between our x and our y, or put another way, it attempts to display how much of our changes in y are affected by x. That particular percentage is r squared. If we square our r, that'll help us explain that, which I'll give you the formal definition in a moment. One quick little note. If you're, let's suppose this r, so let's suppose we had r squared is equal to 0. In this case, we would have, or even, let's go even better, because 0 is kind of boring. Let's suppose we had r squared is equal to 1. In that case, we'd have SSR over SST. The reason why I'm covering this is because you might have it on web work. The SSR over the SST has to be 1. So therefore, SSR is equal to SST. As a note, that doesn't mean they're both 1. Does not mean that. They could both be 1,000 because you could have a lot of data points. What it does mean is that in this case, SSE would be 0 in this case. Which makes sense because if our line is quite literally perfect, with the data we did the regression on, there shouldn't be any error. Now, like I said, if you bring a new data point, you could have some error from that, but you're not going to have any error from the old data points. That said, let's get to the definitions that are going to matter. They say sample correlation coefficient. We'll just go with correlation coefficient R. It says RXY. You can just write down R. It's the square root of our coefficient determination, our R squared. But now you need the sign of B1. You might say, why? Why can't we leave a positive? Let's suppose we have two sets of data points. Let's say one looks like this, and the other one looks like this. One of those relationships is negative. This is why we have to keep the sign, because the sign is supposed to indicate if we have a positive relationship or a negative relationship. Positive means as one increases, the other increases. Negative means as one increases, the other decreases. That's why you have to include the sign. The B1 comes from the regression. Now, the nice thing is, let's say you're given the correlation coefficient in advance. Let's suppose I tell you the correlation coefficient is 0.5. You know that B1 has to be positive. You know what it is. You know it's positive. That's all that matters. Now, the key part about R squared, and this right here, this is what R squared is for. This is why R squared is arguably one of, if not the most important statistics in all of regressions, whether it's linear regression or square or cubic regression, quartic regression, so on and so forth. All the regressions, R squared is arguably the most important. This even extends beyond regressions. You know, if there's such things as generalized additive models, generalized linear models, hedonic models, so on and so forth. For all of them, they always calculate R squared because it basically tells them how well your model's doing. So for example, if we had an R squared of 81%, that means 81% of our variance or changes in our Y is being explained solely by our changes in X. It doesn't mean it's caused by X, but it does mean it's explained by it. So even if X isn't causing it, just knowing what X is gets us a long way to know what's happening with Y. Now the R itself measures the relationship, and this is the absolute value, some rules of thumb here. If R is below 0.2, it's not really much of a relationship at all. If it's 0.2 to 0.4, technically a relationship, not much. So if you wanted to put that in pop terms, 0.2 to 0.4, that was Kanye and Kim for some time. 0.4 to 0.6, it's okay. Nothing too serious. 0.6 point, now really the 0.6 and higher are the ones we're looking for. 0.6 or higher means we got quite a strong relationship going. If you have a really high R value, getting an R above 0.9 is not all that common. If you get your R above 0.95, you've got a really good model in your hands. Now, to pull up the calculator, let's suppose we had an R of 0.9, then we have an R squared of 81%. So 81% of the variance is explained by X, or variance in Y is explained by X. The gold standard for most regression analyses, which pretty much means everything's completely rock solid, typically for predictive stuff, like, say for real estate, you're trying to predict a real estate price that's coming up in the future. You want an R squared of 90% or better. So if we square rooted that, if you've got a correlation coefficient of around 0.95 or better, your model has really, really strong predictive power. That's the gold standard. Now, you don't have to have an R of 0.95. If your R is even 0.6, that's very, very good. What that 0.6 basically means is that there is a clear relationship between these two, and the trend that is indicated by this R is what's going on. We're just saying that, we're not saying our regression will perfectly predict it. So for example, if we go all the way back over here, if we had this second line is going to have a really high R value. It's not going to be perfect. It's going to be pretty predictive, but most importantly, we've established the trend. And oftentimes the trend is what matters the most. If you go into this, those of you that are doing something with finance and business, if you ever work with real estate, you might be concerned about housing bubbles. If you very clearly established the housing prices are going up for no reason whatsoever, just, say something reminiscent of 2005, 2006, that'll be a big indicator. You better jump off the bandwagon before it goes crashing into the ocean. So that said, before I continue on to some word problems, are there any questions about the general concepts behind our correlation coefficients and our R squared? These two are very closely related. If you have one, you can get the other one. All right, I will do one, and then you will do the other one. So let's start with a very boring, mundane one. Let's suppose we're comparing our hours spent studying and impact scores. In this case, we could call this H, and we could call this S, in which case that would correspond to H bar and S bar. We're not calculating that for this problem, but on the exam, you'll see that notation. So we want to interpret this correlation coefficient in the context example. What does that mean? First of all, without the context, just explain what an R of 0.54 means. In this case, we recall that 0.54 means there's a moderate relationship. So we say there's a moderate relationship between hours spent studying and exam scores. If you stop there, you get most of the partial credit, you don't get all of it. The reason why is because you should say that there is a positive relationship between hours spent studying and exam scores, because that R is positive. So in this case, and I'll type it out so it's easy to read. All right. So for A, R equals 0.543 means that there is a moderate and positive. You need both. Don't forget one of them. If you get one of them, then you won't get the full credit. Relationship. Let's make this a little bit bigger. Between hours studying and exam scores. If you want, you can add on to that and you can say a unit increase of 1 hour of studying would result in a higher exam score. That would be extra and perfectly fine. This is the main one. So now we want to compute and interpret R squared. We just square the 0.543. So 0.543 squared. Well, the calculator is 0.295. So if you want to put it in percent form, we could say 29.485%. And I'll type it out in a moment, but what this means is that 29.485% of the variance in exam scores can be explained purely by how much time you spent studying. And intuitively, that makes sense. Studying is a big factor in how well you do. It's nowhere close to all of it. And you can study as much as you want. But if you're an idiot, you're still screwed. On the other hand, there are some people, they just don't have to study. They just walk in, they ace the whole thing. That's why it's important, quite literally, to keep the context in mind. Regardless, I'll go ahead and type this out. So for B, we have R squared is equal to that. So 29.485%, which means that 29.485% of the variance in exam scores is explained by changes in number of hours spent studying. Any questions about where these interpretations came from? Both of these are going to pop up exact same format on the exam. You'll have a different problem and there'll be more parts to the problem, but the regression problem on the exam, you will have two parts like this. You'll have to interpret your R, you'll have to get the R squared and then interpret that R squared. So let's give you a practice one right here. I'll give you about a minute or two to work on this one. And then we'll go over it. Yeah, I'll scroll just a little bit so you can see it a bit better. All right. Hopefully that helps you. If you're at home, you can just use the snipping tool and say, do something like this. That way you can have it off to the side. All right, Jordan, were you able to get all that? Okay. And don't worry, I'll upload the whiteboard immediately after class. I've been uploading the lecture notes, the notes themselves, so you know, this thing, I upload that before class. So the ADA students have that in advance. All right, does anyone need more time for the practice problem? Okay, we'll start with A. You'll notice we're gonna have a very similar format to before. So our R value of 0.844 means, now we recall the rule of thumb, if it's 0.8 or higher, it's very, very strong. So it means that we have a very strong and positive, don't forget that part. Now, if that R was negative, yeah, positive relationship between the temperature outdoors and Lubbock electric bills. Oh, not Brill's bills. Now for part B, we have to get our R squared. So R squared is 0.844 squared. And in this case, that is 0.712336. This is one of the very few things where it's usually expressed in percentage form and not decimals. So I will stick with percentages. So we have 71.234%. And now we interpret that. Pull the text box again, because everyone likes text boxes because my handwriting sometimes isn't the best. So in this case, 71.234% of the variance in Lubbock electric Bills, if you want to say electric bills in Lubbock, same thing. I'm not going to be a grammar Nazi or anything. Unless just your whole sentence is a disaster, but that's a different story. Regardless, 71% of the variance in Lubbock electric bills is explained by changes in the temperature outdoors. You might find that to be interesting. You might say 71% should be 100%. No, some people, some people, they just, when they get home, they spend their whole day reading, nothing electronics. Other people, when they get home, they're on that computer till they go to bed. That's going to require more power. There are some people who do the laundry every 3 seconds. There are other people who throw their clothes on the ground, don't wash them for a good 3 years. They're not going to have as much power there. So that's why it's not 100%. And an important thing I'll caution, both on the exam, the WebWorks, and most importantly in real life, if you see, especially in R squared, that surprises you, don't immediately think that is either correct or wrong. Think about it and try to come up with arguments for and against, like why 71% makes sense and why it doesn't make sense. You'd weigh those two against each other, double check that you're not missing anything. To give an example, if you're doing a real estate analysis in New York City, some of the websites you can filter by the area of the estate, but there's a difference between the area of the house itself and the area of the lot. Many of these, the lots go by in increments of 2,000, whereas the houses go by increments of 500, 500, 1,000, 1,500 square feet, 2,000, 4,000, so on and so forth square feet. If you set it to have a minimum of 2,000 square feet, you're going to miss nearly everything in Manhattan because it's extraordinarily densely populated. And so you're going to get an R squared that's not perfect, but that R squared might look like how it's supposed to be. And indeed, it might end up the same way with the Manhattan stuff. But no matter what your R squared is, you got to think about it for a moment. That said, time for the shortcut. This you're going to want to write down. For the midterm exam number 2, you will be doing regression. I will save you a lot of the computations. I will give you B1. What you're going to have to do, you have to show this. I mean, you don't need to put any of this into Desmos. I wouldn't recommend putting it in Desmos because it's not much. Because you'll be writing down what's already in Desmos. Like you're going to be really writing down exactly what's already there. You might as well put it into a normal calculator and save yourself some time. You still got to compute the 2 means. You're going to have to show yourself computing the 2 means because you're going to have quite a bit of data points. Now, if you want to have something as simple as, if you want to write it as simple as, say, X bar is equal to the sum. Oh, that is the worst summation sign. There we go. The sum of our xi's, and then you say this is equal to, say, I don't know, 1 plus 2 plus blah, 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 plus 10 over 10. I'll take that. Just show me something. Don't just say X bar is 5.5, end of story. At least give me an idea where it came from. Same with Y bar. Your B1, you have to show yourself doing this. Show yourself doing it. Once you're done with that, you have your B1. The last thing you will do, you write it in that form. You have to write it out. You'll just say, here's B0, here's B1 done. Give me the actual final regression equation. This is what usually happens. The only extra step is that you can technically have the computer do the B0 for you. There's really no difference. This is what we do on the job, on the research, and here, at least on the exam. You will be saved a lot of the annoying computations. The web work, you will still have to compute the B1 on your own, but if you use the Desmos process that I showed you earlier, you'll save yourself quite a bit of time. So, actually I already went through an example like that. If you want a further example of how to do this, it's on the practice exam. So if that's said, before I continue, does anyone need more time to write this down? Okay, sorry, I realized I was scrolling a bit too quickly as I began scrolling. So to summarize this far, what'll happen on the exam, it'll be real data. It's not gonna be made up. Many of the numbers on web work are made up. This is not gonna be made up. The stuff in the practice one's not made up either. It's actual real numbers. It'll show you the scatter plot, because technically all those dots, it's a scatter plot, but you've probably seen that before. You'll be given the scatter plot. I'll give you the data points, and I will ask you, compute the two means. After you do that, I'll give you the B1. You will compute the B0. You'll state the regression equation. I will give you R. I will ask you to interpret that R. You'll then give me R squared and interpret that as well. And the last thing you'll do with all that, you'll interpret everything you've done all together. And you'll be asked overall to assess if you think the relationship that is expressed is strong enough to believe that it's actually a relationship and not just pure happenstance. All right. So here's the shortcut example. Do it yourself. Should take maybe 30 seconds to a minute. Actually, probably more like a minute or two. I also want you to use your regression equation to find the predicted value for x equals 2. So I'll give you about a minute or two to do this. Here's the B1. Notice I didn't round it to 3 decimal places because although you can round it to 3 for web work, you use the B1 to get the B0. As you saw before, if you round the B1 too early, you can get a wrong B0. So I'll give you a minute or two to do this. If you're one of the very lucky people who has this exact problem, congratulations, I just saved you quite a bit of time. But then again, that's only if you're watching the lectures, so you deserve it anyways. Make sure when you're calculating your Y bar and your X bar, you should show your work when doing that. Does anyone need more time? Okay. Let's start. We got to get our X bar and our Y bar first. Our X, I'll just write the whole thing out since it's only 5 of them. We have -1, 3, 5, 7, and 10. And we have 5 data points. Our other one, we have 2, nope, not 3, 7, 14, 18, and 26. Now you can do it by hand or use a calculator, whichever you prefer. Either way, neither of them is going to take much time. Oh, you can't see that. There we go. 3, 5, 7, 10. Now we divide by 5, so 4.8. I realize this doesn't look quite like 5, so let me fix that. There we go. Our other one, 2, 7, 14, 18, 26, 13.4. Okay. We're given the B1. We recall that our B0 is equal to our Y bar, so 13.4, minus our X bar, which is 4.8, times our B1, which is 2.22965. So 4.8 times 2.22965, 13.4 off of it. 2, it's positive because I flip the signs around, which makes it easier to enter in here. So now we can round this now if you want, 2.698. And that is our 2.698. So now we put it in our regression form. Notice here, I'll put the hat here, but technically you can't type the hat. You have to write it out yourself. We have our predicted Y value is equal to 2.698 plus our B1. So now we can round it, 2.230 times X. It asks us to find the predicted value for X equals 2. So 2. Oh, come on. Hello. Somehow it crashed a calculator. That's impressive. I'll pull it back up. Couldn't handle it. Too much regression, too much work. 2.23 times 2, add the 2.698. And so our predicted value of Y hat is 7.158. You'll use that process on one of the web work ones. The only thing is that for the web work, you'll have to get the B1 with the Desmos method. It's a bit extra, typing stuff in, but conceptually shouldn't be any more difficult. Are there any questions about this general process or the math? Oh, we have some stuff in chat. I'm sorry, it's not flashing it for whatever reason. Yes, on the exam, I will give you B1. I'll calculate it for you. I'll just give it to you. You'll be told to accept as fact that the B1 is B1. The 2.23 is from rounding this 2.2965. So the reason why we multiplied by 2 is because it's asking us to predict for X equals 2. So I plug that in there. The calculator, which part? The end or the X bars? Because at the end, the end, it was just simplifying this expression. It was just simplifying that. Yeah, multiply and then add, yeah. And, that's easy to write out, so you can. All right. That is all for chapter 14. We are done for today. So enjoy the rest of your evening.